All right. Today we're learning one of my all-time favorite things in math.
Is it easy?
No. Well, kind of. It is, I love it. It's,
We'll get to it.
Not all math teachers love this. DeMoivre's Theorem.
Hey, that looks familiar.
DeMoivre's Theorem, okay? It's in the book. First thing we got to do is cover exponents from yesterday, and that's not that hard if you're starting to get more comfortable with the polar form of complex numbers. So if you're looking at, r equals, no, not r, z equals r times cosine theta plus I sine theta. First, I'm going to give you guys an abbreviation. I wanted you guys to get used to this for one night, but now I'll give you the abbreviation. Those of you who wrote out your homework will get very mad at this. Yes?
You said cosine theta plus I sine theta?
Yeah, that's how it always is.
I think you said times.
I apologize if I did. By the way, since this angle always has to be the same, this is abbreviated as RCIS theta. It's usually said cis theta, even though cosine has a hard C, but we just don't want to walk around saying kiss theta all the time.
Yeah, that's it.
Yeah. So you can abbreviate it this way.
Wait, so that's the abbreviation for the entire equation? Oh my God.
Yes. So last night on the homework, you could have been writing CIS instead of cosine theta plus I sine theta.
Can I do that on here?
Yeah, sure. Okay, now, okay. Exponents. If you take z and raise it to a power, what you do is you raise the modulus, remember that one?
Yeah.
Raise the modulus to that same power, but you multiply the angle by that power. This is a little bit like what happens with logarithms, and it fits the pattern we've had before. Pardon?
Is that a B?
No, r to the n, CIS, n times theta.
CIS.
Okay. Yeah. Now, bless you. Now, this is like yesterday. Remember when we were multiplying, we added the angles? And when we were dividing, we subtracted the angles? So the angles basically always stay one step below on the order of operations. So with exponents, you multiply times the angle. But you raise the r to the power. The modulus, whatever operation you're doing gets performed on the modulus, but the operation below that gets performed on the angle. Does that make sense?
Sure. Well, what if there's a number already in front of the theta?
There won't be, because these are standard angles. I mean, that's a good question though, Drew, but remember, this is a point on a complex plane, okay?
Yeah.
So, this point here, I'm only going to describe it in terms of theta. I'd have to be out of my mind to describe it in terms of 2 theta or 3 theta.
Okay.
When you're using it for something practical like this, practical, the imaginary plane, I cracked myself up. But when you're using it like this for a position, you're not going to slip a 2 theta in just to make your life more exciting.
Okay.
Okay, so here's what this looks like. This is one of those things that's so weird, I like to test it on normal numbers first to see if it works. So for example, if I have 4 plus 0i, okay, in polar form, that's 4 units away from the radius, and that's CIS 0 degrees, right?
Yeah.
That's just sticking out there on the x-axis. Okay, well, if I want to square this, if I decide to square this, that's going to be 4 squared times CIS 2 times 0, which is going to be, what's 2 times 0?
0.
So that's 16 CIS 0. 0 degrees. So that's just going to be 16 out on the x-axis. So 4 squared still equals 16. This rule doesn't blow up in our faces with normal numbers. Okay?
Are we going to have to graph that?
Yeah.
Well, you're only graphing points.
Oh, right.
You know, like I may do something like z equals 4 cis, graph z squared, z cubed, square root, and all that sort of stuff. Get to that in a sec. Okay, now, let's try a negative one. Let's say z equals 4 cis 180 degrees. Okay? 4 cis 180 degrees. if I say what's z cubed, all right, is this positive or negative 4?
It can be both.
Well, what's this one going to be? This based on its position.
Positive.
No, it's 4 cis 180.
Fine, negative.
So on the x-axis, this is
Oh, never mind.
this is 4 units away from 0 in the 180 degrees direction. This is what we would call negative 4 if it were real numbers. Okay?
Right.
Wait,
So if I
why?
cube this,
Wait,
I get, yeah?
why?
Hmm?
It's because he said so.
Well, remember how polar coordinates work? The distance
Well,
is
no, but
positive away from the origin, and then the angle tells you which direction to go.
Wait, is it?
you
Is
have
that
cosine and sine
Yeah.
and I.
Yes. So it's 4 cosine 180 degrees plus I sine 180 degrees. The cosine, what's the cosine of 180?
1.
Negative 1.
Is this a new
Okay.
problem?
What's the sine of 180?
0.
0.
And 0 times 1.
And then there's
0
I.
So this is 4, so this is negative 4 plus 0I
Oh.
when we convert it.
Oh, you just converted it?
Yeah, convert it to rectangular, and I got negative 4 plus 0I.
Okay.
So negative 4 cubed should be negative 64, right?
Yes.
Okay, 4 times 4 times 4,
64.
and it's negative. So if I do, now if I cube this one, I'm going back here, I do CIS 3 times 180. What's 3 times 180 get me?
540.
540. You guys must be skaters or something. So this becomes 64 CIS
Is that negative?
540.
Isn't it negative?
No, because when you're in polar form, you always treat the radius as positive.
Oh, right, I forgot.
Okay.
Sorry.
But which direction is this going? 540,
Goes
180, 360, 540. That is out here in the negative direction.
Is that 0? Or
Yes, this is the same thing as negative 64 is a real number.
Is that oi or I or what is that?
0I.
Okay.
All right.
Remember,
Oi.
So-
negative 1.
Basically what I'm doing, Martina, is I'm checking that this rule works for some real numbers that I know. 4 squared does still get me 16, but I'm calling it 16 cis 0. It's out in the real direction. Okay? Negative 4 cubed, 4 cis 180 is negative 4. Cube it, I get 64 in the 540 direction. So that's 64 out here on the negative x-axis.
When we graph, do we have big numbers like that?
I'll give you the right graph for the test.
Is Z squared.
But we'll get to roots in a second, so we get smaller. Okay, here's how roots
different
work.
examples. Wait. Z squared, that's
I'm sorry, these are 2 different examples. These are 2 different examples, thank you. I should be more
So
clear.
the Z squared is part of the first example.
Yes. Sorry about that. Okay, now, I'm gonna go right to DeMoivre's theorem now.
Hold on, that wasn't DeMoivre's theorem?
No, that's just how exponents work. Okay? Here's the theorem. Because roots work a little bit differently. Okay? This is similar to what's called the fundamental theorem of algebra. You guys remember anyone remember what the fundamental theorem of algebra was? I don't even think I called it that for you guys last year, but did Mr.
Your
Singer?
mom.
Is the fundamental theorem of algebra?
Pythagorean theorem.
No, that's of geometry, darling, sorry.
Oh.
Okay.
The thingamabob.
There's A and B and C or something.
Wow, my God, stop. Okay.
Oh, the
Quadratic
sign.
formula.
Guys, it's about polynomials. Okay.
Oh.
It says if f of x
Yeah,
equals,
that.
okay,
Sure.
a x to the n plus a sub 1 x to the n plus a sub 2 x to the n minus 1. This might be like 5x cubed plus 3x to the squared or something. Plus dot, 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 all the way down to some number. Okay?
They equal 1.
And this is a polynomial. Then n is the number of solutions.
Oh, yeah.
N is the number of solutions.
What is this, like synthetic division?
Now, this is like polynomials, a little bit, but it's you get into that. So this is, so if I have f of x equals, I'll just make one up real quick, x to the 5th minus 4x to the 4th plus 12x cubed plus 52x squared minus 7x plus 14. Okay? How many solutions does this have?
5.
5. This automatically has 5 solutions. Now, some of those